And so I want to tell you about a problem I'm thinking about recently, which is about the structure of low rank matrices, and in particular low rank and sparse matrices. So what do I mean by that? I mean, you're given a matrix. That's an n by n matrix. It has rank R, and think of R as being very low. It has a low rank, and it's very sparse. So by sparse, I mean it has more zeros than what you'd expect from a random matrix. So if this was a matrix over F2, then it has more than half zeros. But if it's a real matrix, having any positive density of zeros would be surprising. And the question is, okay, given these two conditions, what type of structure such a matrix must hold? Okay, so I'm going to talk about three different motivations for asking this question. But in particular, there'll be one basic question that we'll try to understand is that, so here's one natural condition. If you're low rank and you're sparse, then somewhere you should have a big zero rectangle in your matrix. And the question is, how big can you hope for this to be? So while you can think about this question, let me give you some motivations for asking this question. So the first motivation comes from a communication complexity, in particular from the log-rank conjecture. So here the question is the following. So you're given a Boolean function. So let me think of this as a matrix. So this is a 0, 1 matrix. Describing a Boolean function, and the question is, if one player holds a row and the other player holds a column, and they want to compute the entry in this row and this column, how many bits do they need to exchange between them to compute this function? Or equivalently, and sort of there is one simple lower bound observed in the 80s already, that sort of if this matrix has high rank, then you need to exchange many bits. And sort of, so what is a protocol? A protocol is just a way of taking this matrix and breaking it out into monochromatic rectangles, let's say. Here is one partition to a small number of monochromatic rectangles. And the question is, what is the relation between the number of monochromatic rectangles and the rank of this matrix? And sort of, if we look on the number of monochromatic rectangles, then this has to be at least the rank of this matrix, the rank over reals, because every monochromatic rectangle has rank, well, 0 or 1. And the conjecture is that it's not much larger than that. And what is not much larger? So slightly more than polynomial. So let's say rank to some, let's put exponential in log rank to a constant. So this is the log rank conjecture. Asking, is it always true that if a Boolean matrix has low rank, is it always true you can decompose it to a large number of rectangles, to a small number of monochromatic rectangles? So there are many things known about this, but I just want to mention what is the relation between this question and the question of asking about a zero rectangle in low rank sparse matrices. Well, there is a very nice result of Avi and Noam Nissan. So, 95, sort of. Well, they show that no, it's enough to show that there is just one large monochromatic rectangle. So if you could prove somehow that any low-rank Boolean matrix has a large monochromatic rectangles, you can recurse and show that this entire matrix decomposes to a small number of monochromatic rectangles. And sort of the number of rectangles that you will need is really only depends on what you can get for this initial rectangle. So if you can do well on the first step, you can also get a complete decomposition. So sort of here, So now it should be clear what is the relation between this question and the question about sparse low-rank matrices. So here we have matrices over the reals. So the rank here is the rank over the reals. And it's either half zeros or half one. So maybe I have to complement in it. It has half zeros. And what we're trying to show is that this matrix must have a large zero rectangle. And if you can show it, then this will, and if this large is very large, this would prove the log-rank conjecture. Okay? So here, really, the question is about real 0, 1 matrices. Okay. So this is one motivation. Here's another motivation. Studying matrix rigidity. So matrix rigidity, so let's make a definition. So a matrix A is RS rigid if you cannot make its rank low, be below R, by changing at most S entries in the matrix. Sort of, this matrix is high rank, it also remains high rank by changing a small number of entries in this matrix. So if we cannot decompose A as a low rank plus sparse matrix where the rank of L is at most R and S has at most, say, S, non-zero entries. Okay. So, yeah. So this is a definition of matrix rigidity, and sort of this was introduced by Valiant in the late 70s, where he gave this amazing result that rigid matrices actually give rise to lower bounds for arithmetic complexity. So he proved the following theorem. So if A is, so let's say, alpha n, n to the 1 plus beta, rigid. So if you cannot reduce the rank below alpha n by changing at most n to the 1 plus beta entries in this matrix where alpha and beta are some positive constants, then any arithmetic circuit, like the one Avi was talking about yesterday, computing multiplication by A, computing x goes to AX, has to be large. What is large? So it cannot be of linear size and logarithmic depths. And sort of many natural operations, for example, FFT can be done in logarithmic depths and almost linear size, so size n log n. So this really asks the question of, does operations like FFT really require you to use n log n operations, or can you do it better with just linear number of operations? And what Valiant showed is that if you can show somehow that, let's say, the FFT matrix, its rank cannot be made n over 1,000 by changing n to the power of 1.01 entries, this would prove that the FFT operation requires superlinear. It won't be n log n, it will be n log log n, but it will still be something superlinear, much more than what we can prove today. So today, the best lower bounds that we know how to prove for logarithmic depths are linear size, which constant larger than 1, maybe 2 or 3. So this is sort of the motivation that it had later other applications. For example, Razborov used rigidity with some different parameters to try and get a separation in communication complexity. But sort of, unfortunately, we know very little about how to prove that a matrix is rigid. So let me tell you what is essentially the only argument we know how to prove that a matrix is rigid, which is called the untouched minor argument. Let's see what is the correct attribution of it. I think it's from Friedman's work, but I'm not confident about that. So here's the untouched minor argument. Friedman. So it says the following thing. So basically the idea is that you start with a matrix which is full rank. And not only that, all the minors have full rank. So any R by R minor has rank R. And the idea that if you change a small number of entries in this matrix, there's going to be a large minor that is untouched. And if a minor is untouched, it must have the same rank. So this is the untouched minor argument. So here's the theorem. So if A has full rank, and also all minors of A have full rank, then, let's see, A is rigid. Let me see what. So I want it's wrong, the parameters. So basically, if you want, so let's see, if you're changing n squared over r log n over r entries, its rank stays at least r. And sort of the reason, if you ignore, for example, this log n over r, and you just change 1 over r entries of the matrix, then even if you choose a random r by r minor, the number of entries that are going to be touched is like r over 2. So it's going to be r over 2 by r over 2 minus inside it that is untouched. But actually, you can even get this by the Ramkevich. This is the Ramkevich problem. So actually, you get an extra log factor. So this is basically follows from the fact that if you take any bipartite graph representing the entries where you touched, and it has only a very few edges, so this is the number of edges, it must contain a large independent set. And the set is R. And, sort of, unfortunately, that's the only argument that we know. So what is the relation of this to this question on low-rank sparse matrices? Well, so the suggestion is to start with a matrix that doesn't have full rank, to start with a matrix that has low rank. And sort of the idea that sort of low-rank matrices are sort of very noise sensitive to changes. So here is a suggestion to try and do better. So let's assume, so we're trying to prove a rigidity result for rank R, but we're trying to prove a result where we're allowed to change more entries than what we get from this untouched minor argument. So let's assume that the rank of A is R, so it's low rank, but all R by R minors have rank R. Okay? So it's low rank, but it's rigid in being low rank. And it's very easy to construct such matrices over large enough fields, over the reals. So then what do we have? Let's say we can decompose A as a low rank plus a sparse matrix. Well, then S, we know it's sparse, but also it's low rank, because it's a difference from our initial low rank matrix and the assumed low rank matrix in the decomposition. So A has rank R, L has rank somewhere below R. So S is both sparse and low rank. If you can understand the structure of sparse low rank matrices, it might give us a hint on how to show that, this can never happen. In particular, if any sparse low rank matrix has a large zero rectangle, then on this rectangle, our original matrix and this low rank matrix has to be the same. And if this rectangle has size more than R by R, then the rank of L must be the rank of A. So, if any sparse low rank, or let's say sparse and rank R, so this is 2R, matrix has a zero rectangle of size R by R, this implies that the rank of L must be at least the rank of A. Because on this minor, L and A are the same. But the question is, for what parameters of sparsity can we hope to get this type of things? So that's going to be the second motivation. Okay. Any questions, by the way? So if there are questions, please stop me and ask. Okay. So let me go to a third motivation. for asking this question, which is related to constructions of two-source extractors. So, let's talk about Ramsey graphs and two-source extractors. So what is a Ramsey graph? And I'll be talking about bipartite graphs here. So definition. So a Ramsey graph is basically a graph where any large set, or in this case a bipartite set, it cannot be a clique and cannot be an independent set, right? So a bipartite graph H, which is U, V, E, so U and V are the vertices and E are the edges. Let me call it a K Ramsey if it doesn't contain a K by K complete or independent set, or equivalently, if for any subsets S of U and T of V, whose size is at least K, the number of induced edges between S and T, but it cannot be 0, because we do not want it to be the empty set, and it cannot be everything. Okay, so it's somewhere between the two extremes. Okay. And sort of, this has been like a well-studied question in graph theory, in theory, and we have very nice constructions. Sort of, for this bipartite case, I think the best result I could find. So this is a theorem of Barak, Kindler, Shaltiel, Sudakov, and Vigderson. There's a recent one by Ronen, I think, right? It does better. But, no?
Barak, Shaltiel, Rao, and myself.
Okay. Good. Good to have you here. Good, good, okay. Well, they give an explicit construction. For K, which is, let's say, n to the delta for any delta, and even for smaller than that, but let's leave it with that. So for any polynomial size. So n is the size of the set, so let me say the size of U and the size of V is n, so we have n vertices on each side.
This is really easy, and this one, no. It's similar, much smaller than 2 to the power of, 2 to a small power of log n.
Even better.
You mean
The matrix is n by n, right? Not
N by n, yes.
Yeah, so it's something like 2 to the log n to the epsilon.
Even better. Good.
Yeah.
Because I would contrast this with two-source extractors where we could do much worse. Good. Yeah. Yes, because it's rate and
sorry, just
yes.
about that untouched minor argument.
Yes.
So this is if you want to give an explicit construction.
Yes.
Yeah, but the random construction does a lot better.
Yes, okay, that's a very good point.
You don't want to give an explicit. Really, it's not important to give an explicit construction. The big minor can be found by existential arguments.
No, again, I guess you're asking about the rigidity of random metrics.
Yeah,
Oh, I see.
is it true that a random matrix beats this argument?
No, a random matrix it will be very rigid, right? You can change half its entries and the rank won't reduce by much.
No, but not the minor.
Not the minor argument. No, the minor argument is a specific argument to prove that an explicit matrix is. But if you ask just about the rigidity of a random matrix, then it will be very, very rigid.
Yeah. So I mean, this gives an explicit construction of a matrix which is fairly rigid. Yeah.
Is this one. It gives a way of proving for a certain matrix that it is rigid, and you can construct matrices that have this property, that all the mans have full rank.
But But this is not fairly rigid. You don't expect to lose the R in the number of. It's for all applications. This is useless.
Yes.
Okay, yeah.
Yes.
The random one is far, far, far better.
Yeah,
You can erase the R and you can make it.
okay, random one, random matrix, you can expect to be, the rank could be even, let's say, n over 2, and you change n squared over 2 entries or something like that. Maybe you need to do some logging somewhere, but you can change essentially half the entries and the rank won't reduce by more than a factor of 2.
The untouched theorem is sharp.
Well, it is a Rankevich problem, yes, so it is sharp. If you just want to get an untouched minor, then yeah, then it's sharp. But there might be better arguments of proving rigidity than just the untouched minor argument. Yeah, good. So also here, like if you choose a random graph, then you can get this with log n. But we don't know how to do this explicitly. Okay. So now what is a requirement? What is a two-source extractor? Two-source extractor, and for those of you who know it, and I was just talking about extractors that extract 1 bit of randomness, so just to describe it in a similar way to Ramsey graphs. So here it will be very similar to the requirement of a Ramsey graph, except we'd ask much more on the number of edges between any two large sets. We're going to ask it to be very close to what it is in a random graph. So, definition. So, again, we're going to have a bipartite. Graph. I'm going to say this is a K epsilon, the extractor or two-source extractor, if for any two sets, S in U and T in V, whose size is at least K, the number of edges between S and T minus what it should be, which is, well, let's say it's between half plus epsilon ST and half minus epsilon. So it's not only not one of the extreme points, it's actually very close to the middle, which is what we'd expect for a random graph to hold. And even here, if you choose this graph randomly, then this should hold for k being log n. But explicit constructions are much harder to come by. So there is a very simple construction using the Hadamard graph. So the Hadamard construction says we'll identify U and V to just be F2 to the n, and take these edge sets to just be all these pairs U, V with inner product 0. And this is a reasonably good extractor. This is, so K is going to be root n, epsilon extractor. So if you're slightly more than root n, let's say. If you have sets which are slightly more than root the size of the graph, then they have the right number of edges, but this is actually tight because you can choose.
N is not the same n you put in the Hadamard.
It's not the same n. That's good. This is F2. Thank you. This is going to be F2 to the, let's say, R, where R is log n. Thanks. Yeah. So sort of, but for the Hadamard extractor, you cannot hope to do better because this is the limit. If you choose a subspace of dimension R over 2 for U and the orthogonal subspace for V, they're going to have all the edges between them. And sort of, the only constructions where we know which do better than the Hadamard construction, or the best one, is the one by Bourgain. Here is the theorem of Bourgain, which gives a construction where K is slightly less than root n to the half minus epsilon for some small epsilon. And that's the best that we know. So sort of there is a big gap between what we can prove for Ramsey graphs and what we can prove for two-source extractors, sort of. And one of the motivations here was actually a question studied by Eli Ben-Sasson and Noga Tzvi, is can we sort of reduce constructions of Ramsey graphs and show that they must also be two-source extractors sort of by default. Or more particular, can we reduce certain constructions of Ramsey graphs so that they have to be also constructions of two-source extractors? So here is the idea. And again, this idea was in the work of Eli Ben-Sasson and I guess now it's Ron Tzvi from a few years ago. They said, well, many constructions, in particular this Bourgain construction, are formed by actually looking on a subgraph of the Hadamard graph. So are done in the following way. We embed the edges set. Now they're not going to be all the vectors of length R, but just some maybe large subsets of vectors. And the edges are going to be the same. The edges are going to be just all UV, such that the inner product is 0. Okay? And now, what they said is that, well, if we could understand, okay. So let's say that we have such a graph, and we know that this graph is not a two-source extractor. So sort of the idea is, if you can understand the structure of low-rank sparse matrices, here sparse is going to be having significantly more than half zeros, because we order F2, then it will give us a way of automatically using, if you can prove such a construction is a Ramsey graph, it will also be a two-source extractor. So why is that? So let's say here, let's look at this matrix, but this matrix is just the inner product matrix. So just it's indexed by U and V, and it's just the inner product matrix. That's the entries. And let's assume this construction happens to be a Ramsey graph, but it's not a two-source extractor. So if it's not a two-source extractor, it means I can find a large subset of rows and a large subset of columns where the inner products are biased. Meaning I can find a large rectangle here, where let's say the number of zeros is more than half plus epsilon. Okay, so it's going to be, so this is going to be a sparse matrix over F2. It's also going to be low rank because it's the inner product of vectors in F2 to the R. And we're thinking of R as being very, very small. So if this is like an n by n matrix, R is maybe logarithmic in n. So this matrix here is going to be sparse, and it's going to have rank at most R. So if you could prove that sparse low-rank matrices must always contain a large zero rectangle, means somewhere here there is a big zero rectangle, so this graph is actually not a Ramsey graph to begin with for some weaker parameters. So this is the main idea. So the question is, can we prove such results in F2? So this was the motivation. So now let me give you a very concrete conjecture and what's the best you can hope to get just for looking on zero rectangles in sparse matrices and tell you on some partial results on how to prove it. You can delete it also. So here's the conjecture. So let A be an n by n matrix over some field F. So F could be a finite field, could be the reals, could be the complexes, your favorite field. And we're going to assume two things. So the rank of A is low, so the rank of A is R, and A is sparse. So what is sparse? Sparse means, well, if we're over F2, it means having more than half zeros. If you're over the reals, it's having any constant fraction of zeros. So more generally, so the number of non-zero entries, the number of zero entries should be more than 1 over the field size plus epsilon times n squared. So 1 over f is what we'd expect for a random matrix that should have no structure, so some constant larger than that. So think of epsilon as a small constant, 1%. Then A has a 0 rectangle of size n squared over 2 to some constant root r, where this constant depends on epsilon, and you can also make a conjecture on what this constant is, but let's ignore this here. So basically here's the conjecture, and soon I'll show you an example of why that's the best you could hope for. But just to rephrase, just to repeat the conjecture, if you know your matrix has rank R and it's sparse, then we expect the largest size of a zero rectangle, we conjecture it, to be exponentially small in root of the rank. So it's relatively easy to prove this for exponential in the rank, but the conjecture that can do better, to be exponential in root of the rank. Okay, so let me give you an example of why this is the best you could hope for. Example. So consider the following matrix. So I'm going to write my matrix A as the product of an n by r and r by n matrix. Let's call this matrix B. So now it's going to be a rank R matrix to begin with, so we don't have to worry about that. And let me tell you what B is. So B is going to be that the rows of B are all the 0, 1 vectors of weight, let's say, smaller than root r over 10. So the rows of B is all the Boolean vectors whose Hamming weight is small. Small is much smaller than root r. So why is this a good selection? So what are the entries of A? It's just going to be a random element in A. It's just the intersection size of two random sets of size root r over 10. So typically it's going to be 0. Typically two random sets of size root r over 10 don't intersect. Right? So the probability of a random entry that Aij is 0 is actually like 99%. Right? It's very, very likely that two random sets of size root r over 10 don't intersect. But then what is the largest zero rectangle we could hope to get here? Well, it's going to be actually pretty small. So the largest rectangle, the largest zero rectangle, will come by choosing rows to be sets supported on the first half of the coordinates and columns supported on the last half of the coordinates. And sort of what is the size of this rectangle? So obviously it's a zero rectangle, these sets don't intersect. And what is the probability that the set of size root r is contained in the first half of the coordinates, roughly exponentially small in root r? So the largest rectangle is going to have size n squared over 2 to some constant root r. Okay. So this example sort of shows that if you just ask about the size of the largest zero rectangle, and you don't care about the relation between r and n, then that's the best you could hope for, to lose something exponential in root the rank. Now, there are a lot of ways to try and hope to get more refined conjectures. You can ask about more refined structure.
But this should be true only if r is small. I mean, r equals n, it doesn't work.
Yes. Now, this is just ask if you ignore n as a parameter. You just look on the fraction here as a function of r and epsilon.
Yeah.
And you ignore the relation r and n.
So
N goes to infinity, yes. Actually, even, yeah. Obviously, if you could think of all three parameters together, you might hope to do better, yeah. Now, this is just one example to have in mind. You can also try and ask, maybe it's also always true that you can have this type of nice combinatorial reason for zeros. You can have a lot of, you can make a lot of nice conjectures, but let me stick with this specific one here. So, okay, so this is sort of shows that that's the best we can hope for. So what do we know about this conjecture? So we know some things. So this conjecture was actually first asked by Eli and Noga over F2. And so they proved, so Ben Sasson and they proved that, they proved a very weak version of it. So over F2, if, let's say, if 1 minus epsilon of the entries are 0, then there exists a zero rectangle size n squared over, I guess, 2 to the delta r, or delta something that depends on epsilon. Okay. So we are hoping to get something exponential in root rank, and they prove that if you assume that really 99.99% of the elements are 0, then we can still prove an exponential in R, but with an exponent going to 0. Okay, so delta goes to 0 and epsilon goes to 0. Okay. So this is one thing that we know. Here's another theorem. This is also joint work with Eli and Noga. We prove that over F2, if we assume the polynomial Freiman-Ruja conjecture over F2, and let me, for those of you who know it, then you know it, and if you don't, then I don't want to repeat it because I'm not going to be talking about it. So it's some sort of a number theoretic conjecture over F2 that is almost, so that Tom Sanders proved the almost polynomial version of it, quasi-polynomial version, which unfortunately is not enough for this application. Then you can get n squared over 2 to essentially some constant root r over log r. So we get slightly below exponential in r. Well, c is some constant, so r over log r. But again, this is very far from the root of the rank, which we hope to get. And third thing that we know is the recent result that no, over the reals, if we assume that A is a 0-1 matrix, so if we not only assume that it's sparse, but actually that when it's not 0, it's 1, and you can somewhat relax it, but not completely, then there exists a zero rectangle of size n squared over 2 to the root rank log rank. So we can get very, very close to root of the rank if you make this extra assumption that the matrix has some nice elements when it's not 0. Okay.
This almost solves the conjecture under this.
This almost solves the conjectures over reals. So here we have two things. We're over the reals, and we have this condition of being a 0-1 matrix. So I think that this condition can be realized. I think that these techniques can be refined to prove this over the reals, but the techniques here are very geometric, so it's not clear at all if you can use these techniques to do it over finite fields.
And over the reals, it's not as useful as over finite fields? I mean,
it's useful for something, so for rigidity it's as useful, but for this construction of two-source extractors, it's not very useful. So for some of the applications it's useful, and for some it's not.
But you use the fact that the entries are bounded to do some kind of smoothness that you cannot do if they were...
No, definitely the techniques don't extend to finite fields, or to F2 at least. But the result might extend by using some other techniques.
Does the whole when you restrict the B's to be positive or something? So then it's just a set system? And
yes, then it also holds, yes. So yeah, if you have these combinatorial settings where these are subsets of 0, 1, then yeah, then it's also true.
With the root R, exactly.
With the root R. Maybe you need some log R. So. But yeah, essentially with the root R. Yeah, but sort of the question here is now you can allow you cancellations, and what's the best you could do there? So I guess how much time do I have left?
6 minutes.
6 minutes, good. So I want to tell you just a little bit of what goes into the proof here, in the remaining 6 minutes. But sort of, I really wanted to give this talk to motivate people to study this conjecture, both trying to prove the full things over the reals, but also trying to find different techniques of proving it over F2, and also trying to understand more finely what is the structure of low-rank sparse matrices. Okay, let's say we could prove this conjecture. They have this larger rectangle. It's going to give us slightly better result for rigidity. They're going to prove the log to log squared. But I really want to get much better, much more mileage than that. So I think the very simple question is trying to get a more refined understanding of the structure. Okay. So what is a proof sketch of the 0, 1 case. It actually builds upon known techniques and results in communication complexities that were typically used to prove lower bounds, but actually you can use it to also prove upper bounds, in this case, to prove existence of things. So we have this big matrix. And let me assume it's not a 0, 1, it's a plus minus 1 matrix. It doesn't really matter, but it's going to be slightly more convenient. So this is going to be a plus minus 1 matrix. And the proof is actually built upon analyzing the discrepancy of low-rank Boolean matrices. So, definitions of the discrepancy. So this is discrepancy. So let's mu be a distribution over the entries of the matrix. Let's call this matrix A. So the discrepancy is just what's going to be the maximal correlation of your matrix with a rectangle. So the discrepancy with respect to mu of this matrix is just going to be the maximum over all possible rectangles, over all possible subsets S and T, which is a subset of N, over the sum of Aij on I in S and J in T. Yes, now. Good. So basically asking, given the distribution over the entries, can you make this matrix be somewhat, even if initially the matrix is not correlated, unbiased, can you make it biased by restricting to a large rectangle? And sort of the discrepancy.
Mu is not there.
Mu is, sorry, it's good. Mu Aj, thank you. Thanks, Ari. Yeah, mu Aj. You take any entry with the appropriate probability, and the discrepancy of a matrix is just asking what's the worst case, just the minimum of all distribution mu of the discrepancy mu of A. This is a definition of a discrepancy, and it turns out that there is a good understanding of discrepancy of low-rank matrices. So here's a theorem, so it was in, I guess, it was Lineal, Schreiber, Mendelssohn, and Chapman. Thanks. Thanks, Alex. Good. Which proves that, any Boolean rank R matrix has a discrepancy at least 1 over root R up to a constant, basically 1 over 8 root R. So you see this root of the rank popping up. So what is this? So what is the notion of this discrepancy? It says that if here is my matrix and it has rank R, I can find a large, let's say half the entries, well, this is going to be slightly biased. Let's say initially the matrix was unbiased, it was half plus 1, half minus 1. So here on this large rectangle, I can guess that it's going to be, well, the average in absolute value will be more than 1 over root R. Let me ignore constants now, 1 over root R. Okay, so the idea is going to be to try and amplify this thing further. So first thing, one step we do before amplification, if you just wanted to show, so the idea is that, well, here it's going to be slightly biased, we're going to find a large subrectangle that will be even more biased, and more biased, and more biased, and so on. Now, but if we sort of have this bias just with absolute value, we're going to do a random walk. So we're going to need, if this was epsilon, we're going to need 1 over epsilon squared steps. So the first step is just to remove the sign, to not make it a random walk, but sort of like a guided walk. So the idea is very simple. So if this average here is 0, and the average here was, let's say, 1 over root R, we're happy. But if the average here was minus 1 over root R, well, since the average everywhere is 0, then one of the complement matrices must have the average maybe here plus 1 over, let's say, 3 root R. Right? So the average has to be 0. So if one is negative, some complement matrix must be large and positive. So we can always choose a sign, which is going to be important. So we can always assume we can find a large rectangle where the bias is going to be plus 1 over root R. So now let's focus on this matrix. And sort of, it's already biased, so we want to make it even more biased. So the natural thing is to say, well, let's look at the distribution that's going to make this matrix unbiased. So we're going to assign weights to plus 1s and minus 1 so that they're going to be equal probability of plus and a minus. even under this distribution, we should find a rectangle with even more biased. So we can find a large rectangle here where it's going to be maybe 2 over root r. And we can continue this further. So sort of if we make t steps, then we're going to get rectangle of size n squared over 2 to the t. And what's going to be the bias? Well, in the first root r steps, we're going to improve by 1 over root r. But sort of once you get to be very, very biased, and it's natural that the speed of improvement slows down. And you can do the analysis and sort of what the bias here is going to be. If you want to get the bias to be 1 minus epsilon, you need t to be something like root r log 1 over epsilon. So in the first root r steps, you're going to get the bias to be 0.9. In the next root r steps, you're going to get the bias to be 0.99. In the next root r steps, 0.999, and so on. So the speed slows down, but not too badly. So sort of we can do this process and get to a relatively large rectangle, probably exponential in root r if epsilon is small, not too small, but they're going to be very, very biased. But sort of you're looking for really a 0 rectangle. So there is one simple step that you need to do to complete this, which is the following lemma, which says, sort of, if A has rank R, and the probability of seeing 0 is very, very close to 1, let's say 1 minus 1 over 4R, then A has a large 0 rectangle. So that if you know your low rank, and you're very, very close to being 0, then you must essentially be 0 in a large rectangle. And what's the idea? The idea is the following. So here's my matrix. So here's the proof. So we can assume by removing the rows that have too many zeros, so too many non-zero, that all the rows have roughly z fraction of zeros, maybe up to a factor of 2. So all the rows have very few non-zero elements. And it's also a low rank. So let's look on the first R rows. Let's say the first R rows spans the entire matrix. So we know these rows are very, very sparse. So the number of non-zero is just 1 over, let's say, 4R. Then let's say in half the entries, maybe those have some non-zeros elements, but here they have to be all zeros. Right? Because we're assuming that, each one of them individually has very, very few non-zero elements, just by union bound. But they span everything, so you must be, 0 here as well. So you have this very large 0 rectangle. So basically, because you know your low rank, you can stop this amplification process in some small enough epsilon and then show that with one more step you're done. So this is basically the idea of the proof here. And sort of, you can ask, well, is this... So this is sort of like the bottleneck for this proof. So what's the best you can assume about the discrepancy of low-rank Boolean matrices? And unfortunately, that's tight if you ignore, again, the size of the matrix. So if your matrix has full rank, like the Hadamard matrix, if it has rank n, you can show discrepancy is really 1 over root n. But we really don't know if that's tight for low-rank matrices. For low-rank matrices, you might be able to get much better results, and we don't know that. Okay, so.
It's true over F2. That's it. Or you know it.
So what would be true over F2? So, yeah, you can have...
Rank and
Discrepancy.
So you're asking is discrepancy related to rank over F2. So you can
I
have very low rank over F2 and still be unbiased and have a discrepancy. Sort of rank over F2 is not... But you're asking, what if you have rank over F2 and you're biased? Right? So, for example, something like a Hadamard would have very low rank over F2.
So isn't discrepancy, except when you sum it up, you just sum up minus 1 to the power of the entry, so that you get... What's the difficulty in it?
No, I mean, you're asking about thinking of low rank over F2 versus low rank over the reals.
No, if you have a Boolean matrix which over F2 which has low F2 rank, then does it have a large discrepancy?
So I don't think so, because, for example, the Hadamard matrix, Hadamard will have very low rank, like log n rank over F2. But it won't have large discrepancy.
So let's have now we can ask more questions.
You said the untouched minor theorem was tight, but here you also construct an untouched minor, right? So the only extra assumption is that the sparse matrix is also low rank.
Yes.
So that's the only extra thing you're using over...
Exactly. So for example, if this conjecture will be true, then you can get a better untouched minor for low rank sparse matrices. Yes, exactly.
But you said you can only gain this log.
Log, yes. So it's a
So if this conjecture were true, you would gain the log n over the untouched minor.
Yes, it replaces a log with log squared of the thing. So if this was the only gain you can get from it, it would be very minor improvement. I'm thinking that asking for a zero rectangle is just the first step. We really want to understand better the structure of low rank matrices, low rank sparse matrices, much more than just say, oh, they have a zero rectangle. So one question you could ask is it true that always under some change of bases, you can make them to be, look like or be related to the intersection sizes of sets? So the zeros are explained by having sets being disjoint, and the non-zeros by having sets that intersect. And if this is true, you can hope to get much better structural theorems on them.
So another question: I thought over the reals there were better rigidity bounds in the bounded coefficient model.
I think if you're allowing your sparse metrics to also be bounded, then you can get much better bounds.
Which is what the thing you're.
No, because
you said the sparse matrix is 0, 1, right?
0, 1 is, but here I'm not talking about rigidity of it. No, what you're talking about is you can have a matrix that if you change the entries by a little bit, the rank doesn't decrease by much. Right. This you can do. But this is sort of like a different question. Right? So the application of this for rigidity will be for changing just a small enough entries, but with an unbounded magnitude.
But in your result, where you say the sparse matrix is 0, 1, that corresponds to the sparse, that in the rigidity setting, that corresponds to bounded changes, right?
Yes, yes. This result by itself doesn't have new applications for rigidity.
Okay.
Yes.
So another question, so maybe what happens if instead of considering one matrix, you consider a whole vector space of matrices? So this makes it easier. So if you have a whole vector space of matrices that the rank is smaller or equal to R, then it's easier to have untouched rectangle. And I think there are some results about the maximum dimension of low rank matrices, and there the extreme example usually have a huge untouched rectangle. So I don't know if this.
I don't know that, but I'd be happy to hear more about it for you later.